uh, about the middle of the week, and he'll be speaking in the Alpha Street Math Seminar on Friday. I encourage you all to be there. It should be an interesting topic.
What are we going on?
So,
They heard about the
uh, it's supposed to be able to run Krull mix in, so that means you can stack n prime starting counting at 0 high and no higher. Then mention Rx is at least n plus 1, and it's bound to run right twice. So actually, I'm going to start. Let me kind of give you a kind of fun teaser on this. As we go through this, I'm going to prove some junk about polynomials that I need to show this. Ask yourself this at pretty much every turn. Will this or will this not also work in power series? Right? So when I do any of this stuff, ask yourself, whatever I'm doing with polynomials, do you think that'll work in power series as well? So here, this lemma right here is crucial. There. No change. Three consecutive, 3 prime ideals. Say Q0, Q1, 2, all flying over. So this is actually the crucial piece of this. You cannot ever have 3 distinct primes in a row in a polynomial that all contract down in R to the same prime. So basically, set down is impossible. Can't have 3 primes in a row. And so what will this mean? This probably starts to give you a little clue as to where this 2 comes from. Because what this means is the most you could ever get is 2. And of course, let me also point out, note, given a prime ideal, I think this is the last time, or I'm sorry, the last thing we proved last time. Give a prime ideal P inside R, then these both contract P. Remember, this is basically sort of polynomials, if you will, all of whose coefficients come out of P, right? And this is polynomials, if you will, all of whose constant terms. See, both of these ideals, they're distinct because you have X here but not here, and they both contract back down to P. So you can do 2, you just can't do 3. And actually, this helps the idea as well. So why is this true? Well, let's suppose Q0, Q1, Q2, all primes of X. And now, the first thing I want to note is the first thing I'm gonna make the observation, you can always assume that small is PX. Why is this?
Because that's the absolute minimum, but possible.
That's right. So this is because if Q intersect R is equal to P, then P times Rx, which is PX, and Q. And we already know from the limit last time that this is always prime. And so what this really says is PX is contained in any prime that contracts to P. So you might as well, let's just assume that as well, right? Okay. That's the first observation I'm gonna make. And this is actually going to allow me to reduce to the domain case. So now what we have is we have PX inside of Q1, inside of Q2 at the RX level. And these all contract down to P at the R level. Let's pass to we're going to use the correspondence theorem here, right? Because if you look, this translates to the following. This is really cool. Notion. This allows me to go to the, so what I'm doing is basically I'm taking my whole situation, I'm modding out by P of X, right? So there is a one-to-one correspondence between primes of R that contain P and primes of R mod P, right? So this translates to the zero ideal, another prime. These have to be distinct by the correspondence theorem. So what we now have is, this is the zero ideal. This is some prime ideal Q1 hat. Some prime ideal Q2 hat. All in this integral domains polynomial range. So what this has allowed us to do is there exists an integral domain. I'm using the notation, I don't want to call it R mod P anymore, but we reduced this situation. There's an integral domain R, and prime ideals zero inside Q1, inside Q2, at the Rx level, all contracting to zero at the R level. Everybody with me so far? So now what we've done is we've taken this general case, and we said, well, if this situation occurs, then it must also occur in an integral domain like this, right? The integral domain makes my life a little bit easier. What do we know about these three prime ideals? They all contract to zero, right? So in the primes, zero inside Q1, inside Q2, in Rx, there are no constants. Right, these ideals in the polynomial ring here, they don't have any constants, because if they did, it wouldn't contract to zero, right? So look right. There you go. Let S be the set of, oops, that's not that. Let S be the set of all non-zero elements of R, right? This is a multiplicatively closed set. R is an integral domain, right? It's multiplicatively closed, and in fact, it's saturated. And pass to localization. So this is kind of a double threat, isn't it, right? I mean, the first thing we did is we modded out and passed to a domain. Now we're taking a multiplicative set, we're going to pass to a localization. R localized at S is quotient field. And what happens when I take Rx localized at S? KX. Well, actually, let me add a little grammatical flair to this. Localization means polynomial variable, which is KX.
That has Krull dimension one because it's a PID.
What's that?
It's a PID, so it has Krull dimension one.
That's right, right. So you're already at the door, right? But let me explain this a little bit. What does this mean? This means polynomials with coefficients in R over a single denominator class. This means a bunch of fractions of polynomial, right? But guess what? With a polynomial here, so clearly this is contained in this, right? This because this is a single polynomial coefficients in R divided by something S, and so you can write every term as a fraction, no problem. The fact that this is contained in this, well, a typical element here looks like R0 over S0 plus R1 S1X plus Rn over Sn x, right? Now I can collect this denominator. And write this as, for example, R0 S1 up to Sn plus plus R1 S0 S2 up to SNX plus I guess RN S0 up to SN minus 1 XN. All right, just by writing this over a big fat denominator. So now I've got the equality here. And this is X. So now, translation 2 of our situation is this. What we had is 0 inside Q1, inside Q2, inside RX, all lying over 0 in R. And then we localize the crap out of this, right? And so I guess I gotta make sure that nothing screws up, right? So what happens when I pass to the localization here? This translates to 0 inside Q1 hat, inside Q2 hat, inside, well, R localized. Now, remember that I'm using another correspondence theorem. There is a one-to-one correspondence between prime ideals in here that miss the set and prime ideals in the localization, right? Well, all three of these miss S because they all lay over 0. There's no constants in it, right? So that means that these ideals actually must be distinct up here because of the correspondence theorem. These are different. They all miss the set, so these have to be different, right? And so here is kind of the punchline. So we have 3 primes, 0 inside Q1 hat, triple inside Q2 hat in KX. And that's a huge problem because, but KX is because all non-zero primes are max. Before I deliver the coup de grace to this, let me ask you something. Does this work for power series? Okay, where are the problems?
You have containment in one direction here, but not in the other direction.
Right.
So you
In
can't
fact, this is a huge problem right here, power series, right? Because for power series, you get this containment inside here. You almost never get it. Right? For example, if you take the power series. Where 1 over Pn is the nth prime. Good luck finding a common denominator. Right? In fact, in this example, even in this modest example here, if you look at the quotient field of say Z power X localized at the non-zero elements of C, look at the quotient field of that, and then you look at the quotient field of Q power X. The quotient field of this has infinite transcendence over this. It's much bigger. There's actually another failure point. Anybody know what it is? This is a little bit more subtle.
PID.
Well, yeah, there's an earlier failure. Well, so K Power X will get, PID, right?
Oh, yeah.
But there's an earlier failure point for Power Series. This one's also problematic. You,
Assumption about, what the ideals look like in the power series versus the.
oh, yeah, I think you're on the, so. Earlier on, what do we have? When I first started this out, I had P0 inside, or no, I'm sorry, I had Q0 inside Q1, inside Q2.
Can't assume that Q0 looks like it.
Well, yeah, here's the problem. Suppose these all line up with P. What did we do is we said that can assume polynomial case that Q0 is EX, right? Because it turned out that any, and this was important because our small prime was PX and we modded out by PX in the next step. Right? So we said, okay, hey, if you have, in the polynomial case, if you have any prime ideal that contains P, then it, then EX must be in Q, right? It's sort of minimal in that regard. However, this does not hold. I'm sorry, because what we used is if you have a prime ideal that contains the set P, it has to contain the smallest ideal generated by the set in Rx, which is actually PX, which turns out to be a prime. However, for many type domains, this ideal is much, much smaller than this one. And so you can't do that mod out by the P power X question in general. In fact, if you have, let's say, a non-discrete calculation domain, there tends to be infinitely many problems between here and here. So that's another kind of big problem. It's a little bit so. In general, this might happen. So, in other words, there were two big reductions we did in the problem to make this work. Number one, we modded out by PX, so we reduced to the domain case. The next thing we did is we swept out with a localization and reduced it to KX and a PID. Power series makes both of these tricks fail, right, in general. So it's problematic. Okay, questions? Okay, so let's finish this off. So now that we've got the lemma, so I will repeat this briefly. Lemma in Rx, no chain of three primes, cracks, same prime, MLI. So let's prove our theorem. if MR in, then dimension of the power clearance ring is stuck between these two. Okay, so I think that we probably know more about by now, but for completeness, let me just write this. Proof. If well, I'm chain primes and R. So if you have any chain, and we said it's length K and R, then we have the chain. So basically, you just take the smallest ideal that's generated by these PIs up in Rx. And then the cherry on top here is PK, comma X. So this has length K plus one. That is to say, if you have any chain of length K, you automatically get one of length K plus one at the polynomial ring. And so that gives you the lower bound convention. You have to have at least n plus one. The upper bound, of course, is the most interesting. To this end, um, well, let's see. Right, let's put it in this. Um, well, so let's suppose that we have Q0 inside Q1. I'll make it strict so it's interesting. Q2. Well, notice that this gives rise to a chain, let Pi equal Qi intercept R. This leads to a chain at the R level. Now notice that we might have lost our strictness, right? So notice that, of course, T must be less centered in, because of the fact you could mention marks. But
T was the length of the chain up above.
oh, I'm sorry. Break up there. So no, notice T is exactly the length of, but what do we know that, let me rephrase this. The number of distinct elements. Of this chain. Is less than or equal to n plus one. Right, this is what we see. So, of course, what we want to do is we want to get that, what the t is less than or equal to 2n plus one. Right? So how can we, so what's the maximal value? So let's try to maximize t. So how can we do this? We want to make t to be as long as possible and show that, well, we hope it shows still less than 2n plus one.
The more than two teams, that's probably.
Note. At most, two consecutive primes. And prime. Same. From below. Right. So. Maximize t. Length of this chain, we can have Q0, Q1 corresponding to, say, P0, Q2, Q3, P1, etc. Q, let's say 2M, Q2M plus 1. Yes, the start at 0, corresponds to PM. Right. And this last quality, or this last observation is, what you want. So to maximize t, to make this as long as possible, you have to make every pair of two primes contract at the same time here. Okay. And of course, if there's an odd number of primes here, the last one goes to a new one here.
Right. Yeah, and I am right about saying an odd number because we started counting at 0. So, this T must be less than or equal to 2 n plus 1. Because the n is the number of times down here, and this forces the stack to be 2 n plus 1. Hence, n plus 1 like I said, also, this, it has been shown that, in fact, I think they did it with proof for domains. You can achieve this upper bound. This is as sharp as possible. You can always achieve the 2n plus 1 upper bound even with proof of domains. Okay. Any questions? Okay, so, yes,
When you say you can always achieve it, even proof domains, you mean there are even proof for domains where this happens, not that this will always happen given any domain?
that there are proof of domains where this happens. Yeah, that's right. Okay, so talk, as I promised, we're gonna move on a little bit to Dedekind domains here. And this is gonna be our segue into raised operating integers. So definition. So this is the way I'll define it, 821. D is a Dedekind domain. If every non-zero ideal, or you could even say non-zero practical ideal, is invertible. So a Dedekind domain is an Ethereum proof of domain. Remember, proof means every finitely generated ideal is invertible. And of course, finitely generated ideals are the only ones that have a chance of being invertible. So in a proof of domain, everything that can be invertible is invertible. Dedekind domains, if you're an Ethereum, every non-zero ideal has a chance to be invertible, and so is. Dedekind domains exist in abundance. In fact, Z is a Dedekind domain. Any principal ideals domain is a Dedekind domain. Any ring of integers from algebraic number theory is a Dedekind domain. So let me give you my favorite equivalences. I'm going to prove 3 out of 4 of these things are equivalent. So this is theorem 822. R the domain. Following conditions are equivalent. Number 1, R is Dedekind. Number 2, R is Ethereum. Integrally closed. And dimension of R is less than or equal to 1. There are some people that squabble over this a little bit and say, oh, it has to be dimension 1 Dedekind domain. That doesn't sit very well with my aesthetics or the universe. I think it feels are Dedekind domains. So here's the takeaway from this. If you have dimension one, you have an interesting Dedekind domain. If you have dimension zero, then it's a field, right? Two, or I'm sorry, three, sir. Three, R is Noetherian. And RM is a Noetherian valuation. For all M in max spec R. And number four, every non-zero ideal is, in fact, uniquely a product of prime ideals. This is often why I say that a Dedekind domain is a poor person's good, because you might not be able to factor all the elements uniquely into prime elements. Translation, you might not be able to factor all principal ideals into a product of principal prime ideals. But you can factor every ideal into the product of prime ideals. And if some of these are non-principal, that's when you get something that's not equal. So these are equivalent. Every ideal is invertible. Every non-zero ideal is invertible. Every non-zero ideal is product of primes. In fact, it's unique product of primes. Noetherian, integrally closed. Krull mentioned one or less. Three, R is Noetherian, and R localized them is a Noetherian valuation domain for every maximal ideal. By the way, this one might be puzzling. We talked a little bit about this before. This condition right here, R localized M, is always a Noetherian valuation domain. In fact, it's almost the nicest valuation domain you'll get beside the field. That condition does not imply that R is Noetherian. So you can have something that locally at every maximal ideal is Noetherian, but it's not Noetherian itself, right? So this condition here, R is Noetherian at the beginning, is not superfluous, right? It's weird, but you can do it. Y'all remember that domain I built with a tree where I kept splitting things off? That's a good example of one right there. Okay, let's do this. I'm gonna kind of skip over before. I'll leave that kind of as an exercise. Connecting them up. R is Dedekind, so that means that every ideal is invertible. Two. R is Noetherian. All invertible ideals are finally generated. So what does it mean to be Dedekind? It means that all ideals are invertible, hence they're all finally generated, so R is Noetherian. All right, so we've got that. Interval closed. Why is that?
So proof or domain, proof or domains aren't really.
Oh, I like that. I like that. That's a very lazy way to do it. So, and I can get behind that, right? R is proofer. So interval closed. And what else do we got?
I mean, proof is one dimensional too, if you want to do it.
I just,
What's that?
I mean, proof is also less than equal to the.
Not necessarily.
It's not.
No, because all valuation domains are proofer. And valuation domains exist in any dimension. Right? But you're close. I mean, we can kind of take advantage of this again. Since R is proofer, then R localized P is a valuation domain. For all P.
Also, RP is a PID because, R is Ontario, so RP is a Bezier, Notarian Bezier domain system.
Also. RP is Ethereum. Because R is new localization of Ethereum rings. Ethereum. So in fact, it's an Ethereum valuation. So I claim. So P is not zero. P is maximum.
Constant in there and I think everything.
Right, because if not. Then we have zero strictly inside P, zero strictly inside P. And. Remember, our localized P, the prime ideals that live in here are exactly the ones that, the prime ideals that live in our localized P are the prime ideals R that are contained inside P, right? And so if there's a non-trivial prime that's contained inside P, it must survive in this localization, which is PID. But our localized P is a PID. So dimension RP is 1, since P is not 0. So P is maximum. So what have we done? If R is Dedekind, we've got Ethereum, yes, integral flows, yes, dimensions less than. Got that.
You also showed 3 along the way.
Yeah.
What's that?
You also showed 3 along the way.
Yeah. So. What about this? So, yeah, so I've got 1 implies 2 and 3, right? But I'm gonna do 2 implies 3. If R in theory integral close to dimension less than or equal 1, well, I think I've got R in the theory, right? That's automatic. And RM is an Ethereum valuation domain. Well, this is similar to what we did before. Then if you look at RM, this is, what do we know about it? Ethereum. Local. Integral close. Well, but I want to show that, it's a valuation, right? So, so this is. So I guess, yeah, so this is gonna take a little bit more, because what I want to do is I want to show that this maximal ideal is radical, the single ideal, and so forth. So think about this, and also think about 3 implies 1. which I think you're gonna see, you're gonna need the theory hypothesis there, and we'll pick it up next time. Any questions? Any questions? Well, I hope you've enjoyed your time in the sauna. We will see you on.